Okay, so the purpose of this lecture is not to explain some subtleties to the experts. I mean, this is a pedagogical lecture, since it's the first one. I'm going to try to give you more of a colloquium-style general introduction to the field. So to enable you, those of you who are not as well-versed in the field, to follow essentially what's going on. So I realize it's given that we've got a very broad range of backgrounds, this is not a completely obvious decision of where you should draw the line. And what I'm going to try to focus on is actually to give you some intuitive picture of some of the results which are quite familiar for those of you who are not experts, to get some understanding of how things fit together, so that when you hear all of the other talks, it's easier to follow those. But at the same time, you should feel absolutely free to interrupt me at any point and ask about more details. And I hope I'm getting the level roughly right, but you never know with these things. Okay, and the work I'm going to be discussing, to the extent that it's my own, is going back, about a decade. In fact, the time when Arnab, the main organizer here, was a postdoc at my institute, it got me interested in Floquet systems. The field has grown tremendously since then. And as I say, I'm going to be focusing on some of the central ideas. And again, if any of the true experts in the field just feel like leaving, I will not be offended at all, but please don't close the door and not too loud way when you leave the room. But anyway, so as I say, this is this is more like a pedagogical lecture with the emphasis on pedagogical. Okay, so I'll nonetheless skip over the beginning relatively quickly, since that really doesn't need all that much introduction. So, but just to, one of the beauties of the field, of the questions that we're asking in this field, is that these questions can be motivated in an extremely simple way. And I find it, one of the reasons I find it so pleasant to work here is that we're in the 21st century, and if you just think of what's happened in physics in the last 150 years, it seems almost impossible to believe that some of the questions which are still open are so easily posed, and that we can even make some progress in answering them. In part, this is the consequence of some perfectly reasonable things, which is that before the advent of cold atoms, we had very few many-body systems which were coherent on sensible lengths, time scales. And so there was no particular need to ask the question about what really happens in coherent quantum many-body dynamics. And so a lot of the questions that could have been asked already in the 40s, 50s, and 60s simply weren't as pressing from an experimental perspective, and so they were somewhat neglected. And the other one is a much more sociological thing, which is that people who were studying classical chaos tended, in large part for historical reasons, actually to be interested in what we would call few-body systems, right? So billiard, like one particle going around, or then, in the spirit of the Camp theorem, building up higher dimensional phase spaces by coupling together very low dimensional phase spaces, and then being led to think in terms of quantities which aren't very naturally extensible to many-body systems with genuinely high dimensions. So what is called high-dimensional chaos by the chaos community is something that we would normally call few-body physics. And so, as a result, the kind of pictures that were used there, like phase space cuts and all of these pictures where you basically follow the trajectory of a system in phase space in all detail, are things which we simply cannot visualize or treat properly in very high dimension. Okay, and so the big insight from that perspective was you don't do this kind of chaos study. What you do is statistical mechanics instead, and you don't try to understand the system in all detail, but you describe it in a statistical sense. And it was this new perspective which in the last 10 years really has enabled tremendous progress, simply because there are a lot of questions which actually were not so hard to answer in this context. Okay, and the first part of this lecture actually is about this, but I just wanted to give you a little bit of sociological and historical background, to remotivate the system coming from the question coming from the 19th century, where thermodynamics more or less had reached a rather beautiful and complete description of classical systems, and where, in today's language, the two important ingredients which we assume, take for granted in thermodynamics are equilibration and thermalization. So equilibration being the statement that a large system eventually reaches a steady state, which is time independent. And thermalization is the additional observation that the nature of the steady state depends on only very few parameters. So the canonical example here is a little ice cube with a few drops of water around it. And if you see this picture, you've got a very clear expectation that if you came back after a few hours, you wouldn't see this picture anymore. But you'd see something else. And that this something else, if you wanted to know what it is, all I'd need to tell you is the temperature at which this picture is taken. If I tell you the temperature is above freezing, then you expect a larger puddle of water. If I tell you it's below freezing, you expect to find lots of little ice crystals. Okay, so these are two things which aren't even new in the 19th century. I think they were probably familiar to our ancestors who were living in caves, who looked out of their caves in the morning in winter and then had to decide how cold it was going to be. And this is really something that holds as a matter of course, but what this workshop is about and what much research, again, over the decades has been, that this isn't always the case. There are systems which are not described by equilibrium thermodynamics. And one of the questions is why, under which conditions? So which systems don't behave like this, and then also how, that is to say, what do they do instead, okay? And the thing about thermodynamics is that under extremely few assumptions, just using very clear thinking, you can make some incredibly far-reaching statements about the behavior of matter, and it would be nice if we could make some similar, if we could build a similar scaffold for thinking about non-equilibrium physics, but of course, whether or not that's possible is a completely open question. Okay, so then move to the 20th century. Quantum coherent quantum dynamics appeared, as I mentioned, experimentally in large part pushed by the advent of cold atoms. And the hope is somehow that thermodynamics should emerge in such a setting. That is to say that systems which are described, many-body systems which are described by full coherent quantum dynamics should perhaps also behave like thermodynamical systems in the end. So that doesn't have to be like this, because it could have been possible that thermodynamics only emerges provided that the system is no longer fully quantum coherent. After all, thermodynamics usually assumes the existence of a bath, and fully quantum coherent systems do not have a bath. But it turns out that you can actually get thermodynamics out of coherent quantum many-body dynamics. And this is, of course, what is covered by eigenstate thermalization, which was already mentioned in the first talk today. So the basic background here is that if you solve the full Schrödinger equation for a many-body system, you order the states by their energy, and then you plot some thermodynamic observable, or some local observable like a density. Then the statement is that you get a smooth function and not some random sequence of points. And if you want to know what the value of this density is for a given energy, then the statement is, if you looked at the system in a thermodynamic setting where you fix the temperature so that the expectation value of the energy is what's being plotted here, then the observable would be whatever the eigenstate, what the observable is in the eigenstate at that energy. So in other words, if you give me a Schrödinger equation and you fully solve it, which is a tremendously difficult thing to do, then actually you don't need most of the information. The most important part of the information that you need of an eigenstate is its energy, and that's going to determine what the observable is, okay? So in other words, local observables are a smooth function of the energy, and the smooth function is in correspondence with what thermodynamics would measure. Okay, so just as a note of caution, so it's very easy to say these things, but you can easily convince yourself that there's a lot of small print. So for instance, you could ask, how could I ever get by and actually find a many-body eigenstate at a finite energy density? And the answer is quite possibly you will never be able to even prepare one. The reason is that the energy level spacing between two of these energy levels is exponentially small in the system size. And that's because the bandwidth of a many-body system is extensive. It's proportional to the size of the system. The number of states in that bandwidth is exponentially large. Therefore, the level spacing is exponentially small. So by Heisenberg's uncertainty principle, if you want to prepare the state within the accuracy of a level spacing, it will take you a time which is exponentially larger than the system size, and not only you, but also the universe will die before you actually have prepared this eigenstate. So when we say these things, it's not actually clear. So it's clear what we mean on the thermodynamic side, but it's, I think, also clear that experimentally speaking, in a real many-body system, we will never be able to test the eigenstate thermalization hypothesis in an experimental sense, even though, of course, we can have quite a lot of confidence that it's correct based on finite-sized numerics. Okay, but from a quantum information perspective, this is really an important insight, which is to say that you've got a many-body wave function, and again, the many-body wave function is so big, so it's got so many components that you can't even write it down efficiently. That in general, you can't even write it down because you don't have enough paper to write it down on, but most of this information is in fact not needed. What is needed is only the information what the energies of the state. And then you can ask, well, if I don't have these eigenstates, are there other states which can help me access this kind of typical behavior, thermodynamic behavior? And there's a rather large numerical effort devoted to these kind of questions. So if you come across a term like minimally entangled typical thermal state, these are the kind of states where people try to come up with states at finite energy density which are already entangled enough that they actually show all of the behavior that the true eigenstates do, while they're still simple enough that you can actually represent them on a classical computer. Okay, that's basically how these things hang together. Okay, but in this workshop, we're actually interested in the question what happens beyond equilibrium. But this is why I was just pointing out how perhaps to think about equilibrium, then we can ask the question what happens beyond equilibrium. And non-equilibrium is complex. So we are physicists. The next step we're going to do is not look at a non-equilibrium system like a coral reef and say, okay, I've managed to explain equilibrium. Now let's move to non-equilibrium. But what we usually try to do is we find the very simplest setting where we can go beyond equilibrium and still say useful things. Okay? So, and of course, the study of non-equilibrium physics is not something that started a few years ago. In many, many ways, there are many systems which are non-equilibrium systems which are extremely well understood. So in the old days, systems like lasers, the X-ray edge problem, electronic systems, and so on. And then more systematically, perhaps about 20 years ago, people started thinking about other topics, generalized ensembles, or quenches and equilibration physics. And again, there's a lot to say here, and I might touch on some of those today or tomorrow, depending on how things go. One very crucial field is also the study of open systems. So if you take a system which can genuinely exchange energy, particles, and whatever with its environment. So this is something I'm not going to cover at all in these lectures. So basically, I'm really looking at systems which are just described by a self-contained Schrödinger equation and nothing else. And the two non-equilibrium subjects I'm going to be focused on is, first of all, centrally driven systems, so Floquet systems, where you take a Hamiltonian and you make it time-dependent, and the other one is many-body localization, where you add disorder to a system so that it stops being ergodic. Okay, so this is it. Item number one, periodically driven system. So this is the simplest step that we have of going away from equilibrium. So periodic driving is a very common non-equilibrium problem. So many processes in nature are periodic, or at least approximately periodic, even though this one isn't quantum coherent. And it's arguably the simplest case of a non-stationary Hamiltonian. So if you Fourier transform it, rather than getting an arbitrary spectrum of frequencies in the Hamiltonian, you have only a particular frequency and its harmonics. Okay, and so then the two questions to ask is the fate of thermodynamics. So does there exist a generalization of the notion of ensembles to periodically driven system? And then is there a notion of order? And again, to understand this, is there a notion of order? There are many ways of defining order, but perhaps the one that we teach to undergraduates first is in terms of equilibrium thermodynamics, where you basically say, I've got I've got a system, I say vary temperature, and then I'm asking, is the free energy an analytic function of the temperature? Then there are points where it's not. And then at these points, we say there's phase transitions, and we know how to classify them as first order phase transitions, second or higher order phase transitions. And Landau theory tells us under which conditions there have to be phase transitions, and under which conditions they can just disappear as you vary parameters. But all of this is predicated on actually defining equilibrium states. So if your capacity to define an equilibrium state goes out of the window, then the question is, can you still define a notion of order? Okay? And what I'm going to be presenting to you is a way that you can still do this, and then also a way that you can actually get entirely new types of order which don't exist in equilibrium. Okay, so Floquet systems. So as I said, they're non-stationary systems where the Hamiltonian is periodic with a period capital T. That means if you Fourier transform it, you only get frequencies which are commensurate with the fundamental frequency omega 2 pi over T. Okay, so that's it. So this is the class of systems we're going to be looking at. So what is a useful way of describing these systems? One of the nice things about a setting like this is that you can carry over a lot of the intuition that you have from static systems where you diagonalize the Hamiltonian, and then you end up with a complete set of eigenstates and eigenenergies, so the eigenspectrum. And then, since it's a complete set, you can in principle write every time-dependent problem as a combination of the basis vectors that you found like this. And so it turns out you can do the same thing for Floquet systems with the following caveats. Okay, so rather than, so in a stationary system, the time evolution operator for infinitesimal time translations is simply e to the I Hamiltonian times the time by which you're translating the system. That simply comes from formally integrating the Schrödinger equation. You can still define a time evolution operator now over one period, so which takes a wave function at time t and then propagates it by time capital T. And this is basically unitary operation, which is given formally by the time-ordered exponential of the integral of the instantaneous Hamiltonian. Okay, the detail here really doesn't matter. The important thing is that this, since it's coherent evolution, is a unitary matrix, and unitary matrices do have a complete set of eigenstates, just like a Hamiltonian. And in fact, the connection is that if you take the unitary matrix, you can formally write this as the exponential of a Hermitian matrix. So this is just a formal identity I'm writing down here. There's no particular content to this. So in other words, you can take the logarithm of the time translation, time evolution operator, and then call this a Hamiltonian. And this is in fact what's known as the Floquet Hamiltonian. You shouldn't take this too literally. So in particular, even if the Hamiltonian is local at any given instantaneous time, the Floquet Hamiltonian in general will not be a local operator. Okay, so calling it a Hamiltonian is a little bit misleading in the sense that some things that we believe are true for local Hamiltonians are not in fact necessarily true about Floquet Hamiltonians, but nonetheless it has the standard eigensystem. Since you've taken a logarithm, there's ambiguity when you take logarithms about the imaginary part of the logarithm modulo 2 pi. And this is related to the notion of energy conservation. So if you've got an eigensystem, you've got eigenvalues and eigenvectors, and the unitary matrix, basically the eigenvalues are phases, so e to the I times phi, where the phase phi goes from 0 to 2 pi. If you take the logarithm of it, for a static system, it would just be the energy. So basically the rate at which the phase advances in Schrödinger's equation is given by the energy of the system. So here it's known as a quasi-energy, and it's quasi-energy because it's only defined modulo 2 pi. That comes from taking the logarithm. And this, of course, is related to the fact that you no longer have energy conservation. So if the Hamiltonian is static, by Noether's theorem, you have a conservation law, namely energy is conserved, and this allows you to have a well-defined energy for each state. The Hamiltonian is no longer static, therefore, Noether's theorem no longer gives you this conserved quantity, but since it's still invariant by time translation or by time translation by a finite amount of time, just like periodic systems in space, where you replace the momentum by the quasi-momentum, which is only defined modulo reciprocal lattice vectors. Here the energy is replaced by a quasi-energy, which is only defined by modulo 2 pi, or if you take the t into here, which I've dropped, basically modulo 2 pi over t, which is basically just the energy quantum which corresponds to a photon of this frequency omega. Okay, so just to cut this story short a little bit, what you can think of is, say, shining a laser onto your system, and then the system can absorb and emit photons, and the photons that it can absorb and emit in exchange with the laser have photons with this energy omega, and this is the reason why you only have quasi-energy conservation modulo this energy omega. Okay, but other than that, you can still think of a complete set of eigenstates and eigenvectors. And so in particular, we can discuss the behavior of Floquet systems in terms of this, in terms of the spectrum and the eigenvectors of the time evolution operator. So one of the things that you see immediately that goes out of the window from thermodynamics is the concept of equilibration. Because if you've got a time-dependent Hamiltonian, you can't really expect your state at long times to be time-independent. Okay, it could have been, but it turns out in general it's not. But what you can still get is what's known as synchronization. So here the idea is the following. You've got some observable, so this is just an impressionistic cartoon as a function of temperature. And the observable has a time dependence, but in a synchronized system, this time dependence is actually periodic as well. So you basically drive the system with a period t, and the observables at long times also behave as if they exist with period t. So in other words, if you do stroboscopic observations, so at the same point within each period you take a measurement, then the statement is that this sequence of measurements in a synchronized state will be time independent. So there's this what's called micromotion, so that within each period there's a time dependence, but between periods there's no time dependence. Okay, so stroboscopic observations of the observable are time independent is the same as saying that we're sitting in a synchronized state. And for most of what I'm going to be saying, I'm going to be considering the properties of the synchronized state. Okay, and as I'm going to be then talking about later on in the context of time crystals, there are even some settings where you end up with something which is not a synchronized state. Okay, any questions on that so far? All right, so I'm going to now introduce the kind of model Hamiltonians we're going to be looking at, and they have the following properties. So we're going to look at closed systems, that is to say no bath, no dissipation, anything like that. Yeah? 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 Right, so the synchronized state will have the same periodicity as the Hamiltonian. That's right. So I'm not aware of any incommensurate synchronized state, as it were. So really the state is the simplest possible setting. You basically look at your Hamiltonian stroboscopically, it looks time independent. And then you look at your observable stroboscopically, it also looks time independent. That's what I mean by synchronized state. Good. Any other questions? All right, so model Hamiltonians, closed systems. In practice, I'm going to be talking exclusively about one-dimensional systems. And what turns out to be rather important in practice is that the energy density should be bounded. That is to say, locally, I've got a finite dimensional Hilbert space, and locally, I've got a sort of bandwidth which runs between two numbers of order 1, which are given by the typical size of terms in the Hamiltonian. So, but very simply, you can think of realizing this by either having fermions on the side, so you can have 0 or 1 fermions, or hardcore bosons, or spins, which themselves have a finite dimensional Hilbert space. And then just think of either a spin chain or a chain of cold atoms or something like this. Okay. And if you want to think about some concrete realizations, just think of a lattice. And then if you're living actually in cold atom language, then you can have either a particle or not. So that's the particle density. You can have a potential. So the height of the lattice side tells you how much energy it costs to put a particle there. You can have hopping, or you can have two particles interact. And in spin language is exactly the same thing, except for we call things differently. So spin up is a particle present, spin down is a particle absent. A potential is a magnetic field. Depending on whether your spin points up or down, you get a different energy. You can hop the particle, that's the same as an XY exchange, or two particles can interact, that's the same as an Ising exchange. Okay, so whichever language you can prefer, you can think in either of these. So then the Hamiltonian has static and time-dependent terms. And the important thing is the time-dependent terms are periodic. So you're driving the system with a period t, which is 2 pi over omega. And the predication of what I'm going to tell you is that in all of this, details are unimportant. So what do I mean by this? Well, ideally, we'd have a concept of universality, which is what we understand very well in the terms of statistical mechanics and critical phenomena and equilibrium, where we basically say we take all imaginable systems and with probability 1, that is, if you don't have fine tuning, I can associate each system with one of a relatively small number of universality classes. And I don't need to know any details about the system if I want to know its universal behavior. So the favorite example for this is you've got two phase transitions, which are both in the Ising universality class. It doesn't depend on what the microscopic degrees of freedom are or exactly what the Hamiltonian is. The important thing is that you're breaking an Ising symmetry going from one phase to the other phase, and then all the properties of this phase transitions are universal. Okay. We do not have such an understanding for non-equilibrium systems. So the word I like to use is genericity. That is to say, it's universality modulo ignorance. That is to say, we believe that we have a number of criteria which we can use to describe, to predict how a system is going to behave. And what's generic then is that if you tell me what the properties of a given system are according to these criteria, I can tell you what its behavior is going to be. What does the modular ignorance come from? This is not a complete understanding in the sense that if you came up with an example which lies outside what I'm telling you, I'd say, aha, there's one criterion I wasn't aware of, so we have to include this in our set of criteria, and then the classification is going to be complete again until someone else comes along and tells you another distinguishing feature. So you may feel that this is a rather unsatisfactory state of affairs, but of course this is the nice thing about working in a young field which is still developing. One of you may come up with an idea for how, for a property of a many-body system which we aren't aware of yet, which actually is going to be important in classifying them, okay? But so far, we've basically started with knowing essentially nothing to coming up with a set of criteria according to which we can identify different types of behavior. And the different types of behavior I'm going to introducing to you first are basically Floquet ETH, so eigenstate formalization for Floquet systems and Floquet many-body localization. Okay, but before we go there, let me say, okay, actually let's move on to Floquet ETH. So I'm going to take a rather roundabout path there in order to give you the kind of intuition that I historically found very useful when we started thinking about this. Perhaps it's actually not so useful, but I found it useful at the time, so let me give this to you. So as I mentioned earlier, the fundamental difference, which will turn out to be the fundamental difference between Floquet systems and static systems, is that you don't have energy conservation in Floquet systems. And as I said before, since we still have discrete time translations, the energy is defined as conserved modulo 2 pi over t, so the photon frequency that I mentioned before. So the analogy with crystal momentum is actually rather precise here. So you can basically say I've got a system which has got a dispersing system, say a photon mode, which is linear, omega goes as k, and k can take any value, so that you get a linear dispersion like this. Now you put on a periodic potential, and you can think of this periodic potential of doing two things. So one is what I'd call band folding. So basically, you get umklapp scattering, and the momentum pi over a now becomes equivalent to the momentum minus pi over a, because they differ by reciprocal lattice vector. And then you also get level mixing. So let's go through the two of these in turn. So you get this linear dispersion here, and by band folding, so if you normally continued it in this direction, since pi over a is the same as minus pi over a, you can continue this line here until it hits pi over a again. You again umklapp scatter, and then you continue back there. So the dispersion, which was a linear dispersion, now still is a linear dispersion, but it keeps going back into the same Brillouin zone. And the same for the opposite direction. Okay? But in some sense, I don't actually need a periodic potential for this. I could have just decided I'm going to write my continuum as a Brillouin zone, and then I get these many branches, but the states are still exactly the same. If I do have the periodic potential, something else happens, namely in the places where you have these degeneracies or near degeneracies, you now have a periodic potential which actually scatters between these two, and then it opens a gap. So basically, if you've got a periodic potential of size delta, then at this degeneracy point, you're going to split the two modes, the right moving and the left moving one, and you're going to get a splitting here with one mode there, another mode there, and which are split by the size of the potential delta at the momentum, at the size of the potential delta at the reciprocal lattice vector, okay? And this is, of course, in some sense, something that you're extremely familiar with. It's just Bragg scattering. So imagine you accelerate your particle by increasing its momentum. The free particle would simply start, increase its momentum and move in the same direction all the time at the group velocity omega over k, so at the speed of light in this case. But what happens here is completely different. At this point here, it actually suffers Bragg scattering. So rather than moving rightwards, here it's got zero group velocity. If you increase its momentum further, it starts moving the other direction. Okay, so that's what happens in a periodic potential. And now we're going to translate this into what happens in Floquet systems. Okay, in Floquet systems, you get something very similar, except for perhaps this is not conceptually important, but in practice, it's very useful. Unlike in a periodic potential, where basically some energetics tends to set the periodicity of your potential, here the energy axis, okay, so here the frequency that you drive your system with in principle is quite tunable. And so the size of the Brillouin zone basically is something that you can control by changing the frequency of the drive. And one useful way to think about this is that the energy axis, or like the momentum axis here, which was a straight line, where you identify 2 points at the edge of the Brillouin zone, you can alternatively think of this as wrapping the system onto a circle so that this point pi over a literally becomes the point minus pi over a. Okay, so if you do this with the energy axis, if you've got an undriven system where this is the energy axis and here are your states, if you now say my energy axis is actually periodic with period omega, then the driving period tells you what the radius of the circle is, and what can happen in particular is that the radius of your circle may be bigger than the energy width, than your energy bandwidth, then it looks like this. So you basically have put this thing onto a circle, but the two ends of the energy spectrum don't communicate with each other. Whereas by contrast, if your driving frequency is less than the bandwidth, then the high energy and the low energy states in quasi-energy actually overlap. And this distinction is going to be important in what follows. Okay, but other than this, formally it's exactly the same. States with different energy simply get the same quasi-energy, the same way that states with different momentum formally have the same quasi-momentum. Okay, and so I'd like to move on to use this here and give you an idea of how Floquet ETH comes about and what the properties of Floquet ETH are. So we start with this picture here, where we now, and this is important, where we now have a many-body system where the bandwidth is actually infinite in the thermodynamic limit. That is to say, the bandwidth is actually an extensive quantity. So it's an energy density times L. However, the driving frequency is a number of order 1, right? The driving frequency doesn't grow if you make your system twice as big. That is to say, we're always in this setting where the bandwidth of the system is parametrically bigger than the driving frequency. And what this means in particular is if you have an energy level spectrum diagram where this here is the energy, and then I exactly solve my my Schrödinger's equation, and then for a given energy, whenever I've got a state present, I actually draw a little point here. Okay, and then I'm going to change the driving strength on the x-axis. So with 0 driving strength, I actually have the points on the left here. Okay, so let's do this in 2 steps. So I first take my static Hamiltonian, and I solve this, and then I get a distribution of energies. And this distribution of energies for generic, so for a system obeying ETH, has characteristic statistics of level spacings. So if you haven't come across this before, I mean, I'm not going to be able to introduce this in any detail, but the basic point is if you've got systems which are sometimes called chaotic or whatever, or obeying ETH, then the probability of having 2 nearby many-body levels to be very close to each other is strongly suppressed because you've got level repulsion. Crucial observation now is if you do this level folding here, this level repulsion goes away. And the reason is very simple, because if you take 2 states which come from completely different parts of the spectrum, they don't particularly care about exactly what the energy difference is. And so the 2 states can actually live very close to each other. And since a few states live close to each other, that also means that there are going to be considerable gaps between states because the density of states in total is fixed. So if you've got some very short distances between some pairs of states, then you must have long distances between others. Okay, and so this is what's the level folding. A band folding also just by itself. So this is what I said here. Before you actually do the perturbation theory to lift the degeneracy, you basically get these degenerate states which come from band folding. But now the important thing is, if you now drive the system, you actually do connect different states at different energies because they basically get, because you can basically connect the 2 states by absorbing a photon of your drive. And what that means is that you now mix levels with different starting energies. Okay, you mix those levels which are approximately the energy of 1 photon away from each other. So as you switch on the driving, what happens is that you mix these states, and as you start mixing these states, you have lots and lots of level crossings. So here I've shown, say, I don't know, the 50th state, and I'm just tracing the energy of the 50th state as I change the strength of the drive. And what you see at each level crossing, basically a state coming from high energy and a state from low quasi energy mix, and to the right, they basically then a linear combination of these states. And so by the time I have a strong drive here, I will have mixed states coming from a very large region of the original energy spectrum. And so this is supposed to motivate the idea that in Floquet systems, you no longer have the idea of high or low quasi energies, but what you actually have are states which, in terms of the original energy, come from a very broad distance of different energies. Yeah. So from the static Hamiltonian, so this is the static Hamiltonian, and I simply ordered the static Hamiltonian levels by 50. Then I folded it, and then I simply counted 50. Okay? It's driving amplitude, and the y-axis is energy, and each of the spaghetti is a state, right? Okay, and then what you find if you look at the level statistics, so the original system had Wigner-Dyson level repulsion. The folded system without the drive had Poisson level statistics, but then the Wigner-Dyson statistics got reinstated by this level. Okay, there are other ways of seeing this, how this happens, and let me see whether it's on that slide, yeah. Let me perhaps give you the, an even simpler way of seeing this, which is, again, a rationalization of a result rather than a derivation. So basically, I'm showing you a slightly different representation here. So I'm showing you density of states as a function of energy of the undriven system. Yeah? arbitrarily far apart from each other, yeah. Yeah. So, okay, yeah, so I think this is in part going back to what I was saying about generic systems. So when we did all of this work about 10 years ago, it was exactly questions such as the one you're asking now, which made it seem to me like the results that we're obtaining are eminently reasonable, but this is nothing like, forget rigorous derivation, this is nothing like a very reliable derivation sense. If it turned out to be wrong, well, then we would have missed something like what you're mentioning now. I'm not sure the evidence has gotten that much stronger, but people generally believe this result now. But I think the questions you're asking, exactly what is the distribution of matrix elements is eminently relevant. And of course, in many-body localization, these questions play perhaps the central role where you ask, all of these things could happen, but how many of them do happen and how strongly do they happen? And that's an open question. I think at the end of the day here, there are simply so many level crossings that it's good enough at the end of the day, but I don't have a quantitative theory establishing that result, okay? If I may make another sociological observation, I always find it interesting how the original work, one tends to be relatively clear what the strengths and the weaknesses of particular results are. But then with time, as people accept them, they sort of accept them and forget about the weaknesses. And I think many interesting avenues of research sort of remain unexplored because people are not sufficiently aware of the weaknesses of results that they think are robust. Okay. Okay, so here we've got a density of states. Since there are exponentially many states, I plot the logarithm of the density of states. So that is now an extensive quantity. So if you divide it by the volume of the system, that gives you a curve like this in the thermodynamic limit. The properties are that the density of states is very low at the edge of the spectrum and it's maximal around the middle of the spectrum, around zero energy. And now I can try to motivate what happens in a periodically driven system in the language of a quench, where you start the system off in an eigenstate of an undriven system, you start driving it and you ask, where do you end up? And this is now an extremely simple argument. You basically say, if I'm sitting somewhere at low energies, then just statistically speaking, I've got many more states to connect to at higher energies than at lower energies. So this is a logarithmic scale, so I've got exponentially more states to connect to by absorbing a photon than I've got to connect to by stimulated emission of a photon. Okay, so this argument you can obviously run until you hit the maximum in the density of states here. That maximum in the density of states is basically contains the full entropy of the system. So in other words, no matter where you start, you always expect to end up at the maximum of the density of states. And again, there are some assumptions there about the lack of correlations between matrix elements and so on and so forth, and the lack of resonances and the unimportance of coherence bound. Okay, but the statement is if I started very high energy, that is to say, not at zero energy, which would be infinite temperature, but actually at a negative energy, so I start at the most excited state, then I would have stimulated emission of photons until I finally end up here. But in either case, you drift towards the maximum of the density of states. Okay. So I've tried to motivate now with many words, essentially the statement for quasi-energy, there's no notion of high and low quasi-energy, there's just a quasi-energy. And the question whether it's high or low is as meaningful as asking which point in a circle is special. There is no special point in a circle. So now if we simply try to formulate ETH with this ingredient, the question becomes, if I want to have a continuous function, so ETH says observable is a continuous function of energy. Now I want to have a continuous function of quasi-energy, and I'm telling you there's no point in quasi-energy which is special. Well, what function is it which looks like a continuous function which doesn't have any special points? Well, it's simply the constant function, okay? So ETH for Floquet systems says that an observable is a smooth function of energy, and in fact, it's a constant function of energy. Okay, so here I'm showing hardcore bosons in a trap as a function of quasi-energy. The site occupancy is simply given by the average occupancy, which happened to be half filling at this case, and there's no further structure. One way that, yeah? Okay. Yeah. Okay, okay, so first answer to this is at the beginning of the lecture, I said I'm not going to introduce you to any subtleties of the field, and this is one such subtlety. I am going to be talking about pre-thermalization later on, and so you mentioned they've got very long relaxation times, absolutely. So, and much of the interesting structure of what has happened in the last few years is about questions like this, but this is one step in complexity beyond what I'm explaining here at the moment. Okay, and since Anatoli just uses the words infinite temperature, this is licensed for me to also use them here. So often people say, these are infinite temperature averages or something like this. So I personally feel that if a system is not in equilibrium, you don't have a well-defined temperature, and therefore you shouldn't call it infinite temperature, right? So I think infinite temperature is considerably more meaningless than negative temperature. But this is the language that people have adopted, right? And I think, as I say, I think it's not helpful because it implies that there exists a temperature. Really, the statement about infinite temperature average is if you take correlations without any structure whatsoever, so the density matrix is just a unit matrix, then this is what you have, and this is what people call infinite temperature. Okay, any further questions? Yeah? Mm-hmm. Right. That's an excellent question. Yeah, I don't know. This strikes me something worth studying. It should probably be a simple version of the, so I could imagine if you look at, sorry. Yeah, I mean, I was just saying, so if you look at ETH near the centrum of the spectrum, I suspect that's Floquet ETH. No, but you don't need to, you don't, yeah. Right. Right. I mean, you still have, so the fact that you folded only is a polynomial change to the density of states. So this is why I meant, so if you go to the center of the spectrum where you have the same density as you have for any given Floquet quasi-energy, then it's probably the same thing. Okay. I mean, modulo the importance of energy conservation, but this is why I was hesitating. Okay. Okay, any further questions? Good. By the way, people without permanent positions are also encouraged to ask questions. All right, good. Okay, so without any constraints, we get Floquet ETH, and you can ask, is there something else? And if there weren't, the pedagogical lectures would be over now, so you can be confident that there's at least another, another half an hour's worth of things to discuss in this field. Okay, so I should perhaps, it's been a rather contorted way that I've explained things to you. So I could have given you a very simple shortcut, which is based purely on thermodynamics, which is, so the basic idea of thermodynamics is you give me a system, you tell me what the constraints are on it, and then I'm going to maximize the entropy subject to these constraints, and that's going to tell me all I need to know thermodynamically. So all I've done in the Floquet system is taken away the constraint of energy conservation, and in this language, it's completely unsurprising that what you lose is the notion of temperature, okay? Because temperature follows from energy conservation. I think, with that amount of courage and insight, you could simply have at the beginning have said, okay, I'm going to drive my system, I'm going to end up with an infinite temperature ensemble. And that is the correct rationalization of what we're seeing here. So basically, in a Floquet system, you can continue to do standard thermodynamics. All you need to do is throw out the energy conservation and everything else goes through, okay? And so this then already tells us what we have to do if we want to have anything else. We want to have some other forms of constraints which are going to play the role of energy conservation one way or another, okay? Okay, so there are then two strategies for doing something like this. So one is, I no longer have exact constraints, but I may have constraints which are operative on effectively very long time scales. So these are transient phenomena, Floquet engineering, pre-thermalization, so this is what was what was touched on by Anatoli's question. And the other one is you use other sources of constraint to replace energy conservation, okay? So these may be integrable systems. So let me say a few words about this, but that I'm not going to go into any detail. And then the other one is many-body localization, which I'm going to discuss in more detail. Okay, and then I'm going to be discovering pre-thermalization later on as an aspect of spatiotemporal order when we come to that. Okay, so the way I just phrase things is I have energy conservation, therefore I've got temperature, and therefore I can vary things there. So, formally, the way we usually teach some variant of thermodynamics and statistical mechanics is we say, okay, we've got energy conservation, then we introduce some Lagrange multiplier, and then this Lagrange multiplier at the end of the calculation suddenly is called the inverse temperature. Okay, this is something you can do not just with energy, you can do it with any constraint that you have. And so if you've got an integrable system, you can essentially define an integrable system as a system which has constants of motion or conservation laws, which are beyond the normal conservation laws of energy, particle number, momentum, and so on, but there can be an extensive number of them, okay? And so then formally what you can do is you can say, okay, each of these, so I'm going to maximize the entropy subject to keeping the constraint on these conservation laws intact. So rather than getting temperature out of energy conservation, I get one Lagrange multiplier for each of the conservation laws, okay? And this is then gives you what is known as a generalized Gibbs ensemble. So the Gibbs ensemble is the ensemble which you get if you maximize entropy subject to constraints of energy, particle number, and so on. So the generalized Gibbs ensemble is the ensemble that you get when you maximize the entropy subject to all the constraints that are then in an integrable system. This statement is, yeah. Okay, so this is I just explained the generalized Gibbs ensemble, and now the next sentence is, you can do the same thing, at least for classes of Floquet of driven systems, which say free fermion systems, you can drive in a way that they still maintain their block diagonal structure, so that you can still define, say, different momenta, and that you don't scatter between the different sectors. So you can basically take a generalized Gibbs ensemble, and if you drive it the right way, you can get the same thing to be stable in a periodic sense. So that's then a periodic Gibbs ensemble. Question over there? Yeah. These things are related. So in that sense, the answer is yes. So you couldn't get the properties of Floquet systems out of a local Hamiltonian the same way. I'm not sure I can summarize this in a very quick way, but basically, if you want to get an extensive energy difference, what you can do in a local Hamiltonian is locally minimize the energy. And then if you do this, patch your system together out of local blocks like this, you can have extensive energy differences. So, this perhaps one way of seeing why the Floquet Hamiltonian can't be local in that sense. And give you, states which are so different having the same quasi-energy. But I'm not sure that's the, I mean, there are many ways of seeing this. I'm not sure I have a particularly simple way of making the connection complete. Yeah. Question here? Yeah. Oof. Anatoli just mentioned the spectrum, the ground set of a Floquet Hamiltonian. No, I know, but I'm trying to answer the actual question. I mean, so the bureaucratic answer is the energy is only defined modulo 2 pi, so it doesn't matter. But you can still ask, here is the Hamiltonian, I take it seriously. So then the question is there a unique choice? And can I make a choice so that it's actually not bounded below? So I'm, yeah. Mm. Right. Yeah, so is the total bandwidth finite, I guess, is the, yeah. Yeah. You can shift it, but the difference between the top and the bottom. Right. Okay. Yeah, so it wasn't such a stupid question. Yeah, Christoph.
Maybe I have a comment, because actually there are two definitions of Floquet Hamiltonian. There is one you introduced, but actually also in atomic physics, what we call Floquet Hamiltonian is just a original Hamiltonian supplemented with the differential operator with respect to time. And when you diagonalize this Hamiltonian, you obtain spectrum and all this stuff. And then this Hamiltonian is not bounded from below. And this is actually, this is one-to-one to the so-called Dresden atom description in quantum optics. But this is a semi-classical approach to this.
Okay, but is it like a Stark ladder? Or in a sense, that's also not bounded above and below, but nonetheless, if you locally look. That's right, but the question is what you then call physical. I think that, yeah.
So,
Okay. So so what's your definition of entropy? Of half-chain entanglement entropy, okay. Yeah. Sorry? I mean, Anatoli just said that there are some special states which take a very long time, so which you refer to as ground state of the Floquet Hamiltonian. Okay. Right, did we finish this? Okay, so here's the one-slide introduction to many-body localizer. Okay, so this was, I just mentioned the Floquet periodic Gibbs ensemble to give you flavor that the specials, okay, so I talked about universality and genericity. So integrable systems are special in the sense that if you perturb them with a random perturbation, they will generally not remain integrable. So in that sense, they're fine-tuned. So the question then is, are there alternatives to ETH which do not rely on fine-tuning? Okay, and there is the field of many-body localization, which promises that there are alternatives where you can write down Hamiltonians, which give you, which do not exhibit eigenstate thermalizations, and which are robust to random perturbations. Okay, and many-body localization is a field which is not that young anymore, what, 15 years or something like this. Some fundamental questions in the field are still open. So one of them being, does many-body localization exist? So, but at the same time, a lot has been learned about it, and I'm not going to go into these fundamental disagreements, but I'm going to give you a phenomenological description of what ETH and MBL, what distinguishes MBL from ETH. So again, come back to the idea that we have states, some local observable, for a static Hamiltonian organized according to the energy, and then you have the smooth function. So this is ETH. So now we do the same thing for a many-body localized Hamiltonian, and the picture is very different. So here, same thing, local observable, states according to energy, and what you see is that adjacent states look nothing like each other. So this is known as eigenstate chaos. I go from one state to an adjacent state, and the observable changes completely. Okay, there is a very simple cartoon which produces a picture like this, and that cartoon is very simply stated, and I'm going to present it to you now. And then the miracle of many-body localization is that this cartoon is supposed to be stable to all perturbations, and this is something I cannot show to you, in part because it's not known whether it's true or not. Okay, so basically let's go back to our, say, chain of cold atoms, where you have one very large random term. So let this term be the random potential, so that two neighboring sites typically differ by a very large energy. And in fact, let's take this to the extreme case, where we pretend that the only term is actually the random potential, okay? And then you can diagonalize the quantum problem completely trivially. You simply say where the particles sit. That's your eigenfunction. And you add up the energies of the potential, and that's your eigenenergy, okay? Right, so it's basically a classical system which we've declared to be a quantum system. Okay, and then you already see why there's no level repulsion, because there's no level repulsion classical system. But you can also sort of see where the eigenstate chaos comes from. And again, these are impressionistic arguments, but I think you can try to turn them into respectable ones with a finite amount of effort. So if you take two states which are very similar, say they only differ by moving one particle, or a small number of particles, then you see that since there's a huge energy, since the energy level spacing is small, and since the energy difference between the potential neighboring sites is very large, if you keep the configuration very similar, the energy change that you have is actually very large. So in other words, if I simply change the configuration of one particle, I pick up an energy difference which is very large, and therefore two states which look very similar have very different energies. The only way I can get two states which are very close to each other in energy is that I take two particles and I move them in a way that the energy gain by one is essentially canceled by the energy cost of the other, okay? But now the random potential is a very large number, so the chance of having two random variables which are exactly equal and opposite goes down the bigger the range of the random variable is, okay? So in other words, in some sense, if you first take one particle and you move it, then you take another particle and you move it, the sum of two large random numbers is typically a large random number. If you take a third one, it's still a large random number. In fact, you're basically then describing a random walk with a typical step size, which is the typical size of these random numbers. And you're asking, after how many steps do I actually get back really close to the origin, right? And the answer is after very many steps, right? So in other words, if you want to have a set of moves which the energies of which cancel almost exactly, you need a lot of attempts until you finally get back to almost exactly the origin. So this is the statement that if you want two states which are very close to each other in energy, they actually are very different in configuration, because you'd had to move very many particles to achieve this. Okay, so this is basically, one is this direction of eigenstate chaos, the other one is that direction of eigenstate chaos. Okay, so these are, as I say, very simple pictures. Now, the miracle is in all of this that you can argue that if I don't take this classical Hamiltonian, but I actually turn this into a quantum Hamiltonian where I add any type of local terms, I can add a local transverse field, I can add particle exchange, I can add hopping and so on. The statement is that this picture actually is robust, so that you do not immediately get level repulsion, but rather that these states, which are neighboring in energy, are so different from each other that the matrix elements between them are not strong enough to really lead to considerable level mixing, okay? So as I say, whether or not this is true is an open question, but this is the picture behind many-body localization. Okay, and so formally, what happens to the eigenstates in the process is that I told you you can start off with a classical system, and then that's the eigenstate. If you now perturb this, the statement is that the eigenstates get dressed weakly. That is to say, you mix states with eigenstates nearby, but in a way such that the admixture of the eigenstates nearby drops off exponentially with the amount of local change that you do to the Hamiltonian. In other words, to this state, you'll admix a state where this particle here has moved a little bit, or even 2 steps, but the further it moves, the more suppressed this contribution to the dressed wave function is, and the contribution is suppressed in an exponential fashion. And these effective, and then the statement is that in terms of these dressed, and so the bits that we have is this occupied or not. This classical variable then becomes what's known as an L bit or local bit, and the Hamiltonian remains purely classical, i.e. fully diagonalized in this local basis. Okay, so that's the statement about MBL. Okay, now let's look at Floquet MBL. So I would like to return to this picture here, where we've got a finite, where we've got this energy bandwidth, and then we are driving the system with either low or high frequency. So again, I'm going to use a simple cartoon of localization, which you may or may not find useful. And this cartoon is the following. So if you basically say, I've got a system which has got a localization length psi, whichever way you want to define this. And if I cut the system on a length scale, which is considerably bigger than this localization length psi, then in some sense, this cut doesn't know about that cut because it's further than the localization length away. So what I'm going to do is I'm going to study these chunks of the system that I've cut out independently of each other, and then I'm going to say, okay, and the fact that I've actually screwed around at the edges somehow doesn't dominate the physics because the bulk is still the largest part of this, of what I'm considering. The important consequence of this is that once I've got a chunk, the size of which is set by the localization length, then the total bandwidth of my system is actually finite. So now it becomes possible to drive the system in a way that the driving frequency is much bigger than the total bandwidth of the system. So, and this is then supposed to remind you, of the plot I had in the very beginning. So I can now have these 2 settings. So one is when I drive very fast, I actually do not end up ever connecting the lowest energy state with the highest energy state by the emission of a photon, or by the absorption of a photon. By contrast, if I drive the system more slowly, then there are going to be states where this level mixing takes place, where I actually connect the low and the high energy state, and therefore I forget which one in the resulting mixed state, I can no longer say which one was the high and which one was the low energy state. Okay, and so what this basically then predicts in inverted commas is the following. That if I drive my system fast enough, then I'm not going to have any states to connect to by the absorption of a photon, and therefore the system is basically going to act as if it weren't driven at all. So it's basically, I've got a system with a very low energy scale, and I'm shooting some UV photon onto it. There's no way it can absorb the photon, therefore the photon just goes through, and there's no change compared to the static system. Whereas if I do this at a lower case, then I can basically, if you have some picture, flip spins and the process absorbs photons. Then as I do this consecutively, the system heats up. So the prediction then is that we're going to have the driving frequency on one axis, and at very high frequency, we just have the standard static MBL behavior, where at low frequency, where at low disorder, the system is ergodic, and at high disorder, it shows the MBL behavior that I've shown you. So this was low disorder, high disorder. So it's the same thing here, low disorder and high disorder, and there's an MBL transition in between. As I drive more and more slowly, I start unfreezing the states by having matrix elements between low and high energy states on the scale of the localization length. And therefore, the more slowly I drive, the harder it is for the MBL to be stable, and the ETH phase grows at the expense of the many-body localized phase. Okay, so the phase diagram that we predict is that at high frequencies, there's an MBL phase, which, however, needs larger and larger disorder to be stabilized as the driving frequency gets lower and lower. And so here are the 2 cases. Again, this is This is numerics by Achilles Lazaridis in the collaboration with Arnab. So if you drive a system fast, which is many-body localized, you still have this eigenstate chaos here. And if you drive it more and more slowly, the same system then eventually has Floquet ETH, with the observable becoming a constant function, effectively, of the quasi-energy. Okay, yeah. Mm. Okay, and it's a very good question. So first of all, these cartoons shouldn't be taken that seriously. So, you know, it's not like a particularly sharp cutoff. The thing, you know, and you know, whether or not exactly a photon is that energy and so on, all these things are not that sharp, and there's no calculation underpinning this where there's some sort of step function which appears in a very precise way. So the question whether it's possible for a system, many-body localized system, to even exhibit a localized and an ergodic part of the spectrum for a static Hamiltonian, as far as I know, is not completely closed, but it's generally believed that it's not possible to have a many-body mobility edge in a many-body localized system. Okay, so in that sense, it's unlikely that by driving it, you're going to be able to generate something like this. But again, you have to be aware of the fact that none of these results are, you know, super secure. And, you know, it's certainly very, very possible that there is a regime which looks like that, and that it, you know, on very long timescales, and that you'd have to, you know, go to timescales which are experimentally, in fact, unachievable to see that there is no many-body mobility edge, but there may very well be one on, you know, timescales that are experimentally accessible. So these kind of questions are generally quite open. So in work that actually we did with Sidadi a long time ago on a system which wasn't a many-body system, but an integrable one, we found that something could happen where you could even have sort of localized, delocalized, and then a fractal or an intermediate regime, sort of, which was subdiffusive in between. So a lot of things which can happen, and what I'm describing here is really the very simplest zeroth order type of behavior. Okay, there's a second question. Oh, sorry. Yeah. Right. I mean, it would be the same as the L bits. Yeah. Yeah, I mean, at very high frequencies, I mean, in this cartoon, it's just nothing happens, essentially. Yeah. Mm-hmm. Wow. Yeah, I'd prefer not to say anything on that. Yeah, I mean, the question of how and why a Magnus expansion converges and what this tells you, I think, is already sufficiently complicated. Yeah. Yeah. Oh, that's because I stopped drawing the line there. No. Well, I mean, and I guess in part it's because I didn't want to make any statements about the asymptotic behavior of this. Small, what? So, okay, here. So, very weak disorder. So, yeah, right, okay, so this, okay. The statement is, I drew this taking the point of view that in the static situation, there is a finite disorder finite disorder transition between MBL and ETH. And so if you just thought of disorder infinity, of frequency infinity being here, then the statement is that this point literally is here, right? Okay, so if this point were to move left, it would say that there is no many-body localized phase in a static system. So if it were all the way here. Okay. So look, as long as it's not clear what MBL is, whether MBL is a pre-thermal phenomenon, then I can't. But I mean, again, I'd like to emphasize that, you know, this kind of stuff with Arnab we did 10 years ago, and for all the reasons that you mentioned, I think this, you know, we gave a plausible answer, but it's by no means settled, and these questions are to a large extent still open. Okay, so I mean, I don't particularly see a reason to say that Floquet MBL is less robust than MBL. I think if MBL exists, there's a good chance that Floquet MBL exists, but. Okay, so thanks very much for your attention, and I guess we come back tomorrow if you like.